Assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So this problem is looking at a block that is attached to a spring on a frictionless inclined plane. And we are being asked how far from the top of the plane is going to be the equilibrium point for the block. So we need to take a couple of equations into consideration. We're going to be dealing with the force here. The first equation is the force of the weight at an angle, which is force equals mass times gravity sine of the angle. But we also have to take into consideration the force of the spring, which is force equals the spring constant times the position. If it's at equilibrium, those two are going to be equal. Therefore, we can take these two equations and make them equal to one another. So we have mass times gravity sine of the angle equals the spring constant times the position. And we're trying to find the position, so we want to rearrange this equation to solve for x. So we would have x equals mass times gravity sine of the angle divided by our spring constant. And we have these values so we can substitute in, so we actually end up with x equals 14, because mass times gravity is weight, times sine of the angle, which is 40, divided by the 120 newtons per meter, which is our spring constant. And so we get that x equals 0.075 meters. So that is the equilibrium point, or the position of the block. But to get the full, or the displacement of the block, but to get the full equilibrium position, we are actually going to have to take the displacement, which is our 0.075, plus the length of our spring, which is 0.450 meters. So our equilibrium point, our final x equilibrium, is actually going to be 0.525 meters. That is our point of equilibrium. So the second part of this question is asking what the period of the oscillation would be if the block was pulled down slightly and let loose. So we are going to once again create an equation that will allow us to solve for frequency here. So we're going to use our force equals mass times acceleration, and then we'll actually swap out acceleration for mass equals omega squared times x, and then we can exchange the term omega for mass equals 2 pi f squared times x, and we'll make that equal to the force equals kx. And we can put those two equal to each other, so we have kx equals mass 2 pi f squared x, and our position terms will easily divide out, so we can ignore those two, leaving us with the equation k equals m 2 pi f squared. Now we want to solve for frequency, so that because finding the frequency will get us closer to being able to figure out the period. So solving for f, when we rearrange this equation, we have f equals k divided by m square root divided by 2 pi. And we can substitute in our known values here. We know that our k value is 120 newtons per meter. Our mass, since weight equals mass times gravity, and we know that our weight is 14, then our mass is going to be 14 divided by gravity. 14 divided by gravity. So I would put 14 over 9.8, and all of that is divided by 2 pi. So when we solve for that, we get a frequency of 1.46 hertz is our frequency. And our period is 1 divided by our frequency. So when we have 1 divided by 1.46, we get an answer of 0.68 seconds. So that is the period of oscillation.